Texas, counting BPS states.
Great, thank you. So this is going to be a real Coles to Newcastle kind of talk because almost everything I'm going to say originates in ideas developed by either people in this room or people who might be in this room. Antonella Grassi is not here, and some of the things I'm going to talk about are very closely related to stuff she's done, but certainly work by Rod and Tony are very closely related to things I'm going to talk about. So the paper that I'm going to focus on, 9929, with Andrew Knightsky and Mario Martoni. So Andrew is at in the math department at UT, and Mario is a postdoc in physics, and we're all together on the 9th floor of RLM. Has to do with a problem that Andy's been kind of obsessed with for many years, which is counting BPS states. And so maybe I should start with a little bit of a preamble explaining why people in math should be interested in this. Four-dimensional n=2 supersymmetric quantum field theories exhibit a very beautiful interplay between quantum field theory and algebraic geometry. A priori, the subject of our study, the Coulomb branch, of an n equals quantum field theory is a special Taylor variety, which is equivalent due to work by Donaghy and Witten it's the base B of a complex algebraic integrable system we'll call it M to B, whose fibers polarized abelian varieties. And equivalent to that, probably more useful for our purposes, is that there's a local system of lattices, we'll call it gamma hat, with an integral antisymmetric bilinear form on the fibers, and this will in general be possibly degenerate. So that if you mod up either radical the quotient, on the quotient we get a non-degenerate pairing, and such that the complex dimension of B is a half the dimension of gamma, which we will call the rank of the n equals 2 theory. And gamma and the low energy physics at a generic point of B is a U1 to the R supersymmetric gauge theory, and gamma is the lattice of electric and magnetic charges, and this non-degenerate integral pairing is just what's called the Dirac quantization condition.
B is the vector space or an open
Sorry?
Your B.
B is the base of that.
Is it a vector space or an open subset of the vector space?
I will take it to be the vector space. I mean, I'll include some places where certain things become singular. So maybe some completion.
So local system.
Yeah, we'll have monodromies and perhaps complicated behavior around loci of various complex codimensions. Okay. So yeah, so what I said here, somewhere I said generic. So away from those loci, the things I said are true.
But this is really a quantum theory, so that you will have a quantization condition. Otherwise, you won't have the lattice.
That's right. That's right. So I'm just interpreting this lattice as what's called the Dirac quantization condition in the field theory. So there's a very interesting.
And you are not insisting on the pairing to be definite.
Definite. It's skew symmetric. So what does definite mean? It's non-degenerate, but it's
Right,
symmetric.
but you also have a complex structure, because B is a complex vector space.
Yeah.
So you can use the complex structure.
Oh, I mean.
And make it a real pairing to ask.
Right. Well,
that one
yeah.
is definite.
There's a construction for getting yeah. I have to be a little bit selective in what I review, otherwise we won't get to anything. But I mean, we can talk further. I mean, this is the general setup that has occupied many people since the mid-90s when this first came to light. So there are lots of aspects that I'm going to suppress. The one I'm going to so let me just say one more thing before I press on. M is just B star B mod maybe gamma dual, and there's an interesting quantity called the period map, which takes a lattice vector and maps and a point on this Coulomb branch and gives you a complex number. This is called the period map or the central charge. And it's non-degenerate in the following sense, that if D is the exterior derivative on B, and that's 0. So one of the interesting observations about this setup is that M is actually hypercalar.
What is sigma?
Sorry.
I can't quite read it. What is sigma?
What am I saying?
Z.
Z. Thank you, that's better. M is actually hypercalar. And the hypercalar metric is determined by the spectrum of BPS states. Which varies over D, has all kinds of discontinuous jumps, but the resulting hypercalar metric is smooth up, well, it has singularities, but so the spectrum that I'm about to discuss jumps in real codimension 1. Whatever singularities the hypercalar metric might have occur in much higher codimension. Okay, so it's so all this jumping of the BPS spectrum. This is a beautiful observation by Gayota, Moore, and Knightsky. The smoothness of the hypercalar metric is actually puts very tight constraints on how the spectrum of BPS states can jump, and in favorable circumstances actually lets you determine what the spectrum of BPS states actually is. So maybe, since the rest of my talk is devoted to counting such guys, I should say a few words to introduce what BPS states are. So, massive irreducible representations of super Poincare are induced a la Wigner from representations of the little group, the stabilizer of a time-like vector, which in 4 dimensions is just SU2. But let me actually give this a name. L, which in 4 dimensions is SU2. And they decompose into a finite number of irreducible representations of ordinary Poincare, which are induced from irreps of L in the same way. In n=2 supersymmetry, the supercharges, so a super Poincare is a Lie superalgebra. The supercharges are the odd generators, and the Poincare cross the R-symmetry algebra. So let me write this. The super Poincare contains an SU2 R symmetry, under which the supercharges the odd generators of this Lie superalgebra transform the two-dimensional representation. And generically, all of the supercharges act non-trivially on this multiplet, and you get what's called a long representation of super Poincare. But, and for any long representation, well, for any representation, the Casimir, is the mass squared, satisfies an inequality, and it's bounded below by this central charge for a multiplet, BPS, for a multiplet, I mean, a representation of super Poincare with flavor and electromagnetic charge, gamma hat. When this inequality is saturated, some of the supercharges actually act trivially. So we get a short multiplet. I'll be precisely interested in the case where half of them act trivially. And so then we can just label what representations of the little group and the R symmetry induce the representations that come together to form the irreducible representation of super Poincare. Is that clear? So let me give you the answer. Spin J and the trivial representation of SU2R, spin J minus a half, and the two-dimensional representation of SL2R, and spin J minus 1 and the trivial representation. And this is at least for J greater than or equal to 1. These are the representations of the little group cross the R symmetry group, which induce the representation of super Poincare. Okay, and so if you count, this has 4J fermions and 4J bosons in the multiplet. And if J is equal to half, then you just have these guys as a sort of special case. And so we'll call this the spin J BPS multiplet. And so the general question you might ask is, for a given point on the Coulomb branch B, and given choice of charge vector gamma hat, how many spin J BPS multiplets are there? That's actually a little bit harder than what I'm going to be able to answer in any reasonable case, because that number actually jumps in a rather wild way. A slightly better invariant is something called the second helicity supertrace, which I will tell you about over here. So the second supertrace is minus a half trace over the space of BPS states -1 to the 2J3, 2J3 squared, where J3 is the Cartan generator of L. So you can imagine, since this is the second helicity supertrace, you might have wondered what the zeroth and first ones were. Well, the kth helicity supertrace is where you have a power k here. And the first two vanish, obviously. And the first non-zero one is the second. Right? The first one vanishes because the number of bosons and fermions are equal. The second one vanishes because the eigenvalues of the Cartan generator, every positive eigenvalue comes paired with the opposite negative value, so those traces vanish. The first non-trivial one is the second helicity supertrace, and you can amuse yourself if you get bored in the rest of the talk, that the contribution of a spin J BPS multiplet to omega is equal to -1 to the 2j plus 1 times 2j. Okay? That's
going to be a sum
over all of these. All the so these are various different representations of L, right? They alternate bosons and fermions, right? So if J is even, that's a boson. If J is integral, it's a boson. If J is half integral, it's a fermion, right? Well, I mean that's incorporated in this sign over here, right? Here I've labeled the highest weight in the representation. So you sum over all weights. All right, counted with the multiplicities on the right-hand side, and it adds up to plus or minus 2j. As I said, if you get bored, it's like an easy thing to verify. And the nice thing about this is that this second helicity supertrace which maps the points on the Coulomb branch to the integers is locally constant, unlike the raw number of BPS states, and it jumps only at walls of marginal stability. These are places where Z of gamma is equal to Z of gamma 1 plus Z of gamma 2 for gamma 1 and gamma 2 and gamma hat and gamma hat, and gamma is gamma 1 plus gamma 2. Okay, so that's some real codimension 1 locus in B at which this second helicity supertrace jumps, and away from those walls, it's locally constant. Okay. So that's what we'd like to account. That's what actually enters into this hypercalorimetric, as discussed by Guyot-Demore and Knightsky. And so this will be the object of interest. And so it frequently happens in many cases of interest that the integrable system is a Hitchin system And then the BPS states are certain geodesics on the spectral curve let's call it sigma. So M, maybe I should have introduced, well, I'll introduce it. Yeah, so and there are geodesics on the spectral curve C, which, again, according to Timur and Nitsky, are equivalent to what they called spectral networks on C. And they developed an elaborate computational machine for counting these spectral networks as a function of where you are on the base B. But it's extremely hard. Those computations are very involved, involve lots of computer time, and can only be done in the simplest cases. And so what I'm actually going to do is discuss some simple cases. So this counting spectral networks. In part. So let's specialize to some simple cases. So I'm going to be as brutal as possible. The simplest case is where the base is one-dimensional. Okay? So Kim and the dimension and gamma is just two copies of the integers. And even simpler than that is the case of conformal theories. So we could spend another lecture saying what's a conformal theory, but for present purposes, all that really means is that the base B has a C star action on it. And the upshot for us is that there are no walls of marginal stability. So, I mean, the orbit of C star consists of 2 points. It's the origin and everything else, and so there's no room to have a wall of marginal stability for just those orbits. So, as long as I stay away from the origin, every point away from the origin is just as good as every other point. Okay. Great. So, Algerius, Martoni, and collaborators classified all the rank 1 conformal cases. And we'll focus on 3 of them. The so-called E6, E7, and E8 Minahan-Nemeshansky theories. So there are many, many realizations of these theories in physics or math. I mean, every physics realization has some kind of mathematical analog. So since we're in Hitchin system central here, let me tell you a Hitchin system realization of these things. Well, one of many Hitchin system realizations of these things. So this is called this is a M is a Hitchin system for group G. I'll say what G is in a second. On the three-punctured sphere, where, call that C, where phi, the Higgs field, is allowed to have simple poles with nilpotent residues, acupunctures. And so let me just make a table. In the E6 case, we'll take G to be SL3. In the E7 case, we'll take it to be SL4. And in the E8 case, we take it to be SL6. And then the triple of nilpotent orbits, where phi, in which the residues of phi have to lie, are 3 copies of the regular orbit. In the E6 case, 2 copies of the regular orbit and 1 copy of the orbit labeled by the partition 2 squared. And then in the E8 case, 1 copy of the irregular orbit, 1 copy of the partition 3 squared, and 1 copy of the partition 2 cubed. These are all nilpotent, yes. Right, I said 3 nilpotents. Right, and so these are kind of there are many other realizations even within this class, but these are sort of as it were, the simplest such realizations. The flavor lattice, gamma flavor, in these 3 cases is the weight lattice of some group. In this case, it's SU3 cubed mod Z3. In this case, it's SU4 squared cross SU2 mod Z2. And in this case, it's SU6 cross SU3 cross SU2 mod Z6. And as groups, these things sit inside, respectively, E6, E7, and E8. And in fact, they sit inside those groups in such a way that the weight lattices actually coincide.
And what about gamma hat? Does it have also an interpretation as a weight lattice?
So gamma hat. So the quotient of gamma hat by gamma flavor, right, is just 2-dimensional.
Yeah, but
right?
so this extension, does it have any weight interpretation?
Probably. I mean, you could probably tell me. So I don't know offhand, but I mean that's a fine question, right? So the quotient is this 2-dimensional thing. Gamma. What notation did I use? Yeah, gamma, an element will be an electromagnetic charge. And so given some representation of E6, E7, or E8, some choice of electromagnetic charge. Here I've done things so that P and Q are co-prime. That defines what I mean by N. Given given a representation of E6, E7, or E8, an electromagnetic charge, how many spin J BPS multiplets are there now I don't need to say where I am on the Coulomb branch.
So do I understand correctly that if you take the two-dimensional Hitching systems corresponding to these guys, they only have one singular fiber, which is the nilpotent cone, and nothing else?
That's right.
And
so I'm staying away from the singular fiber.
Right.
I'm just
but what's going to happen if you take other subgroups of maximal rank in ADE series?
So these guys claim to have classified all of the cases that can occur, and they use a very beautiful connection to F theory to do that. So in all of these cases, the fiber of the integrable system is an elliptic curve, right? Because we're in rank 1, and so they ask, and the base B here is one-dimensional. So you're asking how many different ways can an elliptic fibration degenerate over the base, and they, that's in the wheelhouse of many people here. So I'm just focusing on these 3 cases. They have a whole table of all of the possible cases where there's just one singular fiber and right. Okay, so that's what I am going to try to elucidate. But using this spectral network story,
how do you understand these groups that you get in terms of the configuration?
which ones? This one or this one? So, I know what they, okay. So these things sort of come manifestly. These are what are called the flavor symmetries, manifest flavor symmetries associated to the punctures. Something that I could probably explain to you after the talk. It plays an essential role in the stuff we've been discussing, and we'll discuss the rest of the week. So at some point I need to explain that. But so this side is so to speak manifest. Each of these guys has a flavor symmetry SU3. These guys have a flavor symmetry SU4, and this one has a flavor symmetry SU2, and so on. There's an SU6, an SU3, and an SU2. Okay, so the manifest flavor symmetry is, so to speak, manifest once I tell you which nilpotent orbit I have. The enhancement to this non-abelian thing, it's already non-abelian. The enhancement to this exceptional thing is some piece of magic that I would need a different lecture to explain.
I would be modest on the left. But are you saying that just from seeing the integral system, just the family of the curves, you can deduce those
Yes.
flavor groups, or do
Yes.
you need also to choose the representation? And then,
No. This purely just comes from the Hitchin system data. It's the way in fact, Ashwin basically talked about this story here because the mass deformations that he was talking about are precisely the Cartan of this flavor symmetry group. So I have the advantage that he already came and gave you a lecture on that, even though you didn't know at the time that that was what he was telling you. Okay. So, right, yes, I was going to write it right here. So Hollins and Knightsky so maybe this time I'll actually give a reference. 1607-01743, did the E6 case for simple, for easy choices of charge vector, electromagnetic. So, for instance, P and Q equals 1, 0, and things like that. The more elaborate looking charge vector, the harder the computer computation that they have to do, and they rapidly run out of steam. So it's very, very complicated, rather difficult. But they did, and there's no, at least in the spectral network approach, no direct access to the spin of the BPS representation that you get, or the combination of spins. So they'll tell you how many BPS states there are, or rather what the contribution to the second Felicity supertrace is for a given representation R.
Isn't there a paper by Dolokhov, Moore, and Longkey which says that you can actually get a protected spin character if you're from spectral networks where I remember you have to remember some orientation data?
Yeah, no, this is what they're doing. This is exactly that computation. I'm just saying, it's saying yes, you can, and actually doing it can be a world of difference. Okay? So yes, you can. So in principle, you can do any of these things. In practice, it just gets very hard very rapidly. Okay? So the answer is yes. But as I said, there's no direct access to the spin J. But what they observed was that omega for the charge vector, which is n times a primitive lattice vector, is divisible, is always divisible by n. And if you look over here, you see that's suggestive of what they call the spin purity hypothesis. Namely, that J is just n over 2. Right? So that for given representation R and charge vector NP, NQ, you only get BPS multiplets of spin n over 2. Right? And for that reason, the second Felicity supertrace is always divisible by n. Okay, great thought. And we'll, but as I said, this is really hard. So what we decided to do was see whether we could do these computations a different way and maybe get a little bit further. So I should say that Nitsky has a student toiling away at the E7 case. And she will eventually, I'm pretty sure, write a paper, but it's hard work. Oh, well, and there are a couple of other things I should say. So there's this spin purity hypothesis. Another thing that they found was that for each of the charge sectors that they looked at, there exists BPS states for every primitive gamma i.e. for n equals 1. And they also observed an exponential growth of the multiplicities with n. So again, they couldn't examine very many primitive vectors. 1, 0 is easy, 1, 1 is a little bit harder, things get rapidly more and more difficult. But all of the ones that they did examine had these properties. Okay, so what did we decide to do? What we did was we decided to look at a different presentation of the same physical theory, namely as a D3 brane probing an E-type 7 brane, or in the F-theory language, D3 brane probing an elliptically fibered Calabi-Yau twofold fibered over this base B. With a 4-star, 3-star, or 2-star singularity over the origin.
The top line over the F-theory line, is that in type 2A or is that in M-theory?
This?
Yeah,
This is in type 2B.
2B.
Okay, so the first line and the subsequent line are supposed to be synonymous, even though they sound different. Okay, one is supposed to be some sort of shorthand for the other. But the second line is the place where you can do algebraic geometry.
So you didn't say that in the table, but are you saying it now that your singular fibers for the Hitchin system are E6, E7, and E8?
I didn't say that in,
You had three two-dimensional Hitchin systems with a single
Right.
singular fiber.
right.
Are you saying now that that singular fiber is E6, E7, and E8? Well, that's what it seems to us written there.
Sure seems that way, but as I'm about to explain, the realization looks rather weirdly different. So I have to think about that. Surely that must be the case, but I haven't really.
The answer is no.
What? The answer is no?
6078 is about the mass parameters and the flavor problem of this. He's talking about the Coulomb branch.
Yeah, I'm talking about the Coulomb branch, but he's asking about, I mean, it is true that the Hitchin system, the previous realization,
Yeah, there's no
right?
Hitchin system in the story though.
No,
There's no Hitchin system
but
in this story.
he had
but
a
in
singular
the Hitchin
fiber in
system-
the Hitchin system.
That's right, and I didn't say what the
And it's
singular
an elliptic
fiber
for
was.
surface, so we can say what type of the singular
Right.
fiber.
Okay, yeah.
Yeah, I didn't say what the singular fiber was. It seems quite reasonable that it's the same singular fiber as occurs over here, but I haven't really thought that through.
I mean, he said that the gauge groups are whatever,
But
SU3,
you don't
SU5,
specificate
SU4, and
No, it's not,
The-
well,
not the
it's,
gauge
I mean,
group,
it's just a local.
The structure
I mean, it's
groups
just-
for the Hitchin system are SU3, SU4, and SU6.
I just have one singular fiber
That's
at the
what-
origin,
But,
so.
but the
I-
singular
I-
fiber,
it's
the
not- the
important
base
cone
isn't
could have a
compact.
different type. It seems that he's saying it has to be
If you
E6, E7,
compactify it,
E8.
say it to be Calabi-Yau.
Well, if I compactify it, it's certainly not conformal, because I have the C star action of the base. Right. What? That's a thing I could compactify to. So then I'd have a pair of these, and then each of these stars would be something like what's called a half K3 by some friends of yours. Right. Anyways, Right, and so in this presentation, the BPS states are strings of type NPQ stretching between the D3 brain and the 7 brain. Equivalently, in the F theory description, these are holomorphic curves on X with n boundaries on the D3 brain. And so the problem becomes one of counting holomorphic curves. Well, when I say holomorphic, remember X was hyperkähler, so it has a whole P1's worth of complex structures, right? So these are two real dimensional surfaces which are holomorphic in some complex structure. Which one depends precisely on what the central charge is. Okay, so they're holomorphic in some complex structure for X, and they're in some relative homology class in this geometry. Now, as stated, X is singular, so this is a thing beyond my ability to try to count. But now we use the C star symmetry to our advantage. We take the D3 brain very far away from the origin. And then what we do is what the physicists would call mass deform the singularity. We take these singularities and we split them into a collection of I1 singularities. Okay? And then we can actually count more intelligently.
But you cannot do that by keeping the homogeneity.
That's right. So that's right. So I break the C star, but I break it by only a little bit because the D3 brain is very far away. Okay, and so this, if I only break it by a little bit, this won't. Remember, these things are supposed to be locally constant numbers, and so nothing will happen to the second helicity supertrace when I deform the singularity of the central fiber a little bit, as long as the D3 brain is sufficiently far away. So I'm using the conformal invariance to do that. So let me just say what things deform into. I see that my time is rapidly running out, but let's see what I can do. So, E6, E7, E8, this was 4 star, 2 star, constituent I1s. So these are all conjugate to what's in the physics literature called the D7 brain, right? An object on which a fundamental string can end. Analogously, there are things called PQ7 brains, which are conjugate under SL2Z to the D7 brain. And those are things on which PQ strings can end. Okay? So the collection of PQs are as follows. There's 5 D7s, and then 1 7 brain of type 1 minus 1, and 2 7 brains of type 1 1. Here you get 6 1 0 plus 1 1 minus 1 plus 2 1 1, and here you get 7 1 0 plus 1 1 And the idea is that I have my D3 brane far away. Over here I have maybe I should use colored chalk or something for the 7 brane. I have my collection of 7 branes. And I have, maybe in some canonical presentation, the branch cuts all run vertically downwards. So these are my 5, 1, 0 guys. This is my 1, -1 guy. And here are my 2, 1, 1 guys. And if I start with my D3 brane over here, let's say I have some string, and I'll just pick a particular charge vector. Let's say I pick 3, 0. Okay? And these strings can form junctions where the sum of the charges adds up to 0. And so this 3, 0 string can split like this and become a 4, 0 string over here. And then it could split again and with multiplicity 2, which I'm not going to denote, and become a 2, 2 a string over here. And then it could split like that and become, and now join onto these guys. And this collection of strings, if you work it out, just turns out to correspond to the highest weight of the adjoint of E8 with electromagnetic charge 3, 0. And you can write down, having gotten the highest weight guy, you can actually get all of the other guys by adding what I call neutral string junctions, and you pad out the full adjoint representation of E6. So the idea is that you take, so a way of labeling these strings is just by saying that I have Qi, let me just call these A, some number of strings ending on the ith brane of 7 brane of type 1, 0, some number of strings ending on the 7 brane of type 1, -1, and Q1 and 2, some number of strings ending on the 7 brane of type 1, -1. And the charge must now satisfy n times p is the sum on I of the QAI plus QB plus Q1C plus Q2C, and NQ is the sum on I and QIA minus QB plus Q1C plus Q2C. And the intersection pairing in this relative homology turns out to be just some quadratic pairing on this vector of Q's. And so I can, in light of the time, maybe I won't write out the detailed formula, just some quadratic, some bilinear expression. If I take 2 vectors of Q's, it's some bilinear expression in them, which I can write out, or I can show you the formula in our paper. And you can ask, well, what collection of Q's actually has a holomorphic representative in some complex structure for X, right? So the Q's represent relative homology classes, right?
I missed, what was the boundary condition for the relative homology?
So they have n boundaries on the D3 brane.
So the D3 brane is the infinity of the heat?
It's very far away.
Okay.
very far, as far away as
So you
want.
take a smooth fiber far away.
That's right.
And you put M boundaries on that fiber.
That's right. Right, and then, you know, ending on these severing branes, remember, these severing branes are the thing where some PQ cycle on the fiber shrinks to 0. And so, you know, the projection of the curve ends there, right? It kind of wraps around. Is that clear?
Mhm.
Right. Okay, so that's the picture. So what are the conditions that you might, that you need in order for there to be a holomorphic representative? Well, the first thing, which is obvious, and in fact was known back forever, this sort of string network formulation was formulated by de Wolf and Sweebach and various collaborators way back in the late 90s, I think. The first most obvious thing is that the intersection pairing of J with itself, because X is Calabi-Yau, this is just 2G minus 2 plus N, which had better be greater than or equal to N minus 2. That's kind of obvious, because right? That's necessary, but it turns out it's not sufficient. And now I will present an experimental result, which is that we found that if you...
How can you possibly say what is sufficient without knowing what the Driscoll factor is?
Well, what we did was we computed for lots of cases, and every case where Knightsky and his student could do the spectral network computation, and they, you know, spent a lot of late nights, or she spent a lot of late nights doing it, they kind of came up with the same answer as we do. So let me tell you what the other condition is. It's an obvious one. For J and J prime, in the same PQ sector, but different N. Now J and J prime, now those corresponding curves are supposed to be holomorphic in the same complex structure. If I have two curves that are holomorphic in the same complex structure, then their mutual intersection number should be non-negative. As I mentioned previously, there's always a representative for n equals 1, the primitive charge vector. So let's just assume that guy is holomorphic, then that determines all of the higher guys for higher n that are allowed. And it turns out that precisely reproduces everything that Knightsky and Hollins and Knightsky and his student are able to do in the spectral network computation, plus predictions for arbitrary charge vectors, E8, which they still don't know how to do, and so on. You can just do, and the computations they're just instantaneous. They take no time whatsoever. In a simple Mathematica notebook, you can just churn out arbitrary predictions. The disadvantage of this story is that whereas we can turn things out, so we learn one thing that they don't have, namely the genus of the curve. Right? So this is an invariant that was not in their story at all. But we don't learn about the multiplicity. So this is a sufficient condition to say that there exists at least one spin J multiplet in this charge sector. But we don't have very much information about how many of them there are. So one thing we learn there's a very natural interpretation of this spin purity hypothesis, because n is now the number of boundaries on the D3 brane. And there's a sort of very natural pattern that appears in the old string theory lore about BPS states coming from string worldsheets with boundaries. If you have a single boundary, you get a hypermultiplet, which is j equals a half. If you have a cylinder, which is two boundaries, you get j equals 1. And so obviously, if 1, 2, you know, it always works for any integer, you always get spin j as n over 2, right? I mean, that's clear, right? So it's a natural sort of intuition for where the spin purity hypothesis might be coming from. It also, oh, well, yeah, there's a whole nother story. There's some beautiful, how late? I've already gone 10 minutes late, so maybe I'll skip. There's some other so beautiful but mysterious patterns in Hollings and Knightsky's work, which become abundantly clear when you do this story. It have a completely straightforward explanation. And you can do E8. We're thinking about trying to study higher rank cases. It's in principle all very easy. The thing that's lacking in our approach is we don't know how to count the multiplicities of these things. We do know that genus 0 always occurs with multiplicity 1. Genus 1 always occurs with multiplicity 2 or 3. After that, things start to get murky. But in principle, there should be a well-defined multiplicity. The number of curves in this relative homology class that are holomorphic in the given complex structure, that should be a well-defined problem, which I think there ought to be a mathematical solution to. I just don't know what it is. So I apologize for running over time and being somewhat schematic in my conclusions, but there's a lot more to say, and maybe we'll say it privately. Thank
What about the rank 1 SCFT cases where you don't have this kind of spin junction picture? So in the Argyros-Martoni classification, we have like E6 where you don't break to I1 to the 8, but
That's right.
other things. And then I don't have the D3 brain picture, right? So
well, so then you don't have a picture where the where you just get a collection of I1s.
Right.
Right. So I think you still have this D3 brain. The trouble is you need to work a little bit harder if you want this string junction thing. So the nice thing about when it reduces to I1s is then X is smooth, right? So I can do, I can study homology classes in smooth varieties. Remember, I'm a peasant, so I can only do simple things. So that's a simple thing I know how to do. When you don't actually produce just a collection of I1s, X is still singular, so you need to think about these things, on a singular variety. And that takes some more powerful machinery. Antonella tells me that they know a lot about how to do that. I was sort of hoping to hear from her about that, but she's off organizing, I'm told.
So I was wanting to get a better idea. So you can do the E6, E7, and E8 cases via this F theory. What about classical groups? Is there also a version of this construction there?
Well, so as I said, what we were concentrating on here was rank 1. Okay, so there is a story for SU2, which was already done, and there actually the spectrum of BPS states is quite simple comparatively. I mean, here you get BPS states occupying for all n, right, and in fact an exponential growth in the multiplicities according to these guys. So it's quite a complicated spectrum. The SU2 with 4 flavors, which is also a rank 1 conformal theory, it's got a relatively simple spectrum of BPS states. If you want to go to higher rank, then things become much more interesting. One thing that happens in higher rank is you do get walls of marginal, you can get walls of marginal stability. And so you need to decide where, so now, so higher rank means in this case more D3 branes. Okay? So now it depends on where they are, right? And there are different, chambers depending on, where they are oriented relative to the, 7 branes sitting at the origin. Okay? So, so that's a more complicated story where, thinking about that, the one real disadvantage in developing this technology is we don't have the crutch of this spectral network computation, because those are just too hard for higher rank. So, it's nice to be able to have some wild idea and just be able to check it against an honest computation. But we don't have that to avail ourselves in the higher rank case.
So, you assume that the mass parameters are all very small compared to the Coulomb range.
Right.
What happens to this genus G curve if you start varying the mass m? I mean, does it just be deformed in some way, or? Presumably the spectrum is going to jump if I move the masses too much.
Oh, yeah.
How might that-
So, I mean, you can sort of see that here. The idea is when the D3 brane is very far away,
Yeah.
right? What I have here is an NPQ string ending on the D3 brane,
Yeah.
right? In fact, all of this, string junction stuff occurs close to the 7 branes, right? And after I've gone a certain distance away, it's just a single NPQ string stretched off towards the D3 brane.
Yes.
And as long as, the D3 brane is far enough away, that's going to be the situation.
Yes.
And then this is close enough to being the holomorphic curve that I want, that I'm counting these guys. Now, so these intersection numbers are also locally constant, right? So I literally get the holomorphic guy when I set all the masses to 0, right? But then they're hard to count. If I split them a little bit, the intersection numbers don't change, and it's very close, arbitrarily close to being the holomorphic curve that I was interested in.
Yes, I understand that. I'm asking what happens when the mass parameters get bigger.
Oh, well then, yeah, I mean,
So does the topology of the Riemann surface stay the same? Or, I mean, so maybe you can't write down a complex structure with the thing, but does the notion of genus still make sense? Another question I have is, what is the genus in the 4-dimensional physical theory? What is it counting for you, or what is it telling you about the 4D theory?
that's actually a great question. So one of a suspicion that I have, so as I said, genus 0 always comes with multiplicity 1.
Sure.
So I think there's just a unique curve there. I expect the higher genus guys come in families. And what you're getting is, the Euler characteristic of the, moduli space of that family. And so when I'm giving you a number, I'm, not actually literally counting curves, but computing some Euler characteristic of some moduli space of a family of curves. And so, in some sense, that certainly is physical, whether the BPS states, are isolated things or occur with collective coordinates that you have to quantize.
Yes.
Okay. I think that's the answer.